Even though if somebody came in right now, they actually didn't miss anything. That's okay. They missed this. They missed the password. Okay. So we're right in the middle of force mass acceleration, FMA, right? Oh man, it's too bad. Oh. Force mass acceleration, right? And we did it for Cartesian coordinates, and then we did it for normal tangent coordinates, okay? And so in normal tangent, that's what we're in the middle of. You sum the forces, it's mass times acceleration in the tangent direction, which is mass times acceleration in that direction, the change in speed. And then in the normal direction, it's either mass times e squared over rho, or mr omega squared, or rho omega squared. Just depends on, do you have omega, do you have velocity, which one do you have, and then you can use either one of those, okay? We did a brief example, right, of somebody jumping. In this case, the key there was the normal force went to 0. When it goes to 0, then you can solve for that minimum velocity in order to jump, okay? And you can come up with the velocity such that the mass times gravity is canceled out by that centripetal acceleration. Okay, so the next one we're gonna do is this guy right here. Right, we kind of skipped over this one, so I have an accompanying video for this one. Oh, there it is.
Right over the edge. So should I put this T minus 10?
Okay, don't do this. Don't do it. Gotta put that up.
Plan, drive to a predetermined spot on the bridge. Attach a 200-foot-long cable to a parked limousine. The 5-member stunt squad runs the swing end of the cable to the side of the bridge. Each jumper would attach themselves to the end of the cable and then jump, swinging out like a pendulum. Then release the cable and escape before police, Coast Guard, and fire department authorities can capture and arrest them all. The stunt required precise execution. The camera crew in the helicopter is ready. The camera crew below the bridge is set. The 5 daredevils jump.
Okay. Suspense. Is everything gonna be okay? Let's go over here and let's double check. Okay. So they have a cable attached to a limousine, right? And then they jumped off of that. Turns out there's like I found this last night, like a 50-minute like footage of this, just raw footage of the guys from start to finish, like the whole talking themselves up, the planning, getting into the limousine, all attached, because they're all attached to everything. If you're looking for something to do, you can watch that. Okay. Anyways, so back to this. So they jump. Is everything going to be okay? So we're going to say that there's 1,000 pounds of people jump from the bridge with a 200-foot rope. The capacity of the rope is, I kind of changed it to 2,999. I'll explain it. 1,500. I'll explain why it wouldn't be that. Is everything going to be okay? So then they jump. All right. So this one is, right, we're in the middle of the force mass acceleration. So we're going to do a force mass acceleration problem, okay? FMA. So the first step in an FMA problem is to do what? Free body diagram, every time. Literally, I mean, just get into the habit of just starting these things, right? I know you can kind of, you want to jump, you want to skip steps, but don't do it. Just do this every time. It's worth points. Free body diagram, kind of go through the checklist of that, isolate the mass. What do we got acting on this thing? Forces acting on it? Yep. Tension in the cable. We're just going to do it at a random location, some unspecified location as it's falling. Okay, what else is acting on it? Gravity, yep. So this is, yeah, I should put a T on that. That's tension in the cable, and then we have gravity. Anything else? Yeah, there's drag and stuff like that, but we're neglecting drag. Most of our problems, we neglect drag. So that's it. Those are the only forces on it. We're not done with the free body diagram yet, though, because we have to put in angles and dimensions and everything else that's worthwhile, right? So we're going to do this for an angle theta. Right, theta is going to be changing as it's going down, but we're just going to put a random theta. We might as well break this thing into its various components as well, just to kind of make it a little bit cleaner. Oh, we need to define our coordinate system. Okay. Where's our coordinate system at? Thoughts on which one we should use? Right. Normal tangent, right? That'd be a good one. We're right in the middle of that section. So normal tangent coordinate system. So we're going to have Where are they at? Right, which is normal tangent. What do we do for normal tangent? Right? Tangents in the direction of increasing our velocity, right? But it's in the direction of the velocity, so that's tangents. Tangent's going to be going down there. Which way is normal going? Right back towards the middle, right? That's the way that we define it. One is tangent to the path, and one is normal to the path. So our coordinate system is going to go like this. We're going to have something right here, a tangent there, and then normal pointed back to the middle. This is ET, and this is EN hat. And so over here on our free body diagram, this is going to be ET, and this will be EN. Everybody see that? One's tangent to the path, and one's normal to the path. So it's like that. ET is going down, EN to the. So then what I got in the blue there, the little blue there, is just to show, right, that mass times gravity doesn't line up specifically with the normal direction or the tangent direction, so it's got two components to it, right? And this ends up being theta right here. Right, we go theta, not theta, theta. So that's going to be theta right in there. Right? On your free body diagram, you don't necessarily need to break it down into the components. I break it into the components just because it's easier for me to do that. Right? Makes it a little bit cleaner when I go to sum my forces. But that's it. That's anything. Anything else missing from there? I think that should be it. Okay? Second step, write our equations of motion. EOMs. Okay. We'll do the n direction first. Okay, just break it into its different directions. We got some of the forces in the n direction. We have, I'll highlight them over here. We've got this guy right there and that guy right there. Those two forces. So this would be T minus mg sine theta. That's my forces. That's all of them. Right? The component of mg in the theta direction, and the t is all in the n direction. That's equal to mass times acceleration in the n direction. And the acceleration in the n direction could be written a couple different ways. It could be mass times velocity squared over 2. No, not over 2, over r. Or rho, I guess is the way we're writing it here. Or it can be written as m rho omega squared. You could use either form of those things. It just depends if you have velocity or if you have omega. Right? So I'm after t right here. I'm after that t. I know mg. I know theta is going to be changing as we go along. And I know rho, but I don't know omega. So I'm kind of stuck at this point. I'm not done yet, so I just keep going with it, right? So that's in the n direction. Once I get rho, once I get omega, then I can solve for t. Right? So once I get omega and theta, I'll be able to solve for t. Okay? Right now, I don't know those, so I got to keep going. So now I look in one of the other directions. Just keep going. Some of the forces in the t direction is equal to, the only thing we got there is this. Right? That's the only force we have acting in that direction. So that's just going to be mg cosine theta is equal to mat, which is equal to mr alpha. These things are changing, traveling in a circle. So if you look back in a circle, that tangential tangential acceleration could just be written as r times alpha. And so I'm going to solve for alpha at this point. All right, these masses cancel out. Those guys go away. And so alpha is just equal to g times cosine theta divided by r. And what this is an accel, a function of position. Right? Alpha is a function of theta. Right? So that's the same as acceleration, a function of position. Right? So then you go back to what we did for rectilinear stuff, and you look up how you do problems that have acceleration, a function of position. Now, this problem, like in about a week from now, is going to be way easier when we have energy methods. This one just, again, screams energy methods. You're looking at velocity at the top, the energy that's stored, the potential energy stored in those 1,000 people, and then they jump off, and then all that velocity changes or so all that potential energy turns into kinetic energy, and you can solve for the velocity. Right now, we don't have that in our tool set, so we have to do it this way. Okay, you can do it both ways. This way, energy, if you have energy, this one screams energy. But right now, we don't have energy, so we got to keep going. All right, so then to do acceleration, a function of position, we got alpha is equal to d omega dt. You multiply by d theta over d theta. So we get d omega, d theta, dt. This is just omega. Kind of rearrange things here. And we get, that's equal to d omega, d theta times omega. And so we're going to put the d theta over there. So it's alpha d theta is equal to omega d omega. All right, and we can substitute it in alpha right there. So this is just g times cosine theta over r. D theta is equal to omega d omega. And integrate this, and integrate this. This is going from 0 to our omega final. That's the bounds on that one. On the right-hand side, the bounds are going from 0 to omega. What about the bounds on the left-hand side? Where's this thing going to be going the fastest? When theta is equal to what? Yeah, pi over 2. When it's down at the bottom, right? Pretty easy to imagine. The fastest they're going to be going is right down at the very bottom right here, right? And so our theta at that point is going to be equal to pi over 2. So down here, that's what we put as our bounds. And that'll tell us kind of like the worst case scenario. What's the fastest they're going to be going throughout this whole thing? And that's going to be down at the bottom when theta is equal to pi over 2. Okay. What I did at this point, I just plugged this sucker right into my calculator and carry out the math however you want. You get omega is equal to 0.567 rads per second. Okay. Now we have that omega. We know what their angular velocity is going to be. That goes back up. That goes right in here. Right? And once you do that, then you can solve for that t. So let's go ahead and do that down here. T minus mg sine theta is equal to mr omega squared. We'll plug in all the things that we have here. T is equal to mr omega squared plus mg sine theta. T is equal to the mass. It's 1,000 pounds of people, so we have to divide that by gravity. So this is to be divided by 32.2. That's all the mass. The radius is 200 feet. Theta is 0.567. That squared plus 1,000. I'm running out of room. 1,000 times sine of pi over 2. That's what we put in for that theta. Because again, we're trying to figure out the t down at the bottom. That's going to be the worst case scenario. And if you solve this t T is equal to 3,000 pounds. So is everything going to be okay? No. Because the capacity of that rope was 2,999, and so it's going to break. Where is it going to break at? Right down at the bottom, right? This is why when I used to have it at being 1,500, it would actually break before it made it to the bottom. It would break somewhere on the way down. But in what we're going to see in the video, it actually breaks down at the bottom. So it would need to have a capacity really close to that 3,000, okay? Right. Again, this one's actually pretty straightforward if you have energy methods. This gets a little weird when we have to solve for the acceleration, we solve for alpha, and then we have to do the chain rule, and then we have to carry it out to find the velocity down below. Once you get energy, like I said, this problem will be a little easier, but we don't have it yet, so we have to keep doing it this way. Okay, any questions about that? So let's go back to the video. I have to say, no one dies. They do get injured, though.
Slow motion
That one
replay
doesn't
of the
look too
failed
bad.
stunt shows that the Daredevils did not have enough pressure on the cable when they jumped from the top of the bridge.
That's not it, right? Like they said that it was like the slack and then the impact load, but all that slack is gone at this point, right? And then they're still attached. So it wasn't the slack that they're talking about. It was the centripetal acceleration.
Weighing almost 1,000 pounds reach the end of the cable, the tremendous force snaps their lifeline. For the jumpers, the first injuries are whiplash from the cable. The second and more powerful is the impact of the water 200 feet below the bridge.
That view, when you see from above, that looks, because a big splash afterwards.
Glory is unconscious, her neck broken. Jeff is not breathing. His neck is also broken. Chaos takes over as the jumpers and the boat crew stare at death all around them.
Good to hear the end here.
The pendulum death swing claimed no lives, and today all of the injuries have healed.
There we go. See, everybody's okay. The death swing, but nobody died. So, I don't know. Okay. So while we're on this subject, I'll show you some other ones. Oh, what do I got? I got a thing named for it. Sounds, structures 2. Hold on. Bridges, coefficients of Coriolis, dynamics, EPALs. My favorites, dynamics, flywheel, gears, gravity, light. Oh, yeah, rope swings. Okay, this is in Russia. It looks to me that it is in, Chernobyl possibly. That's in the Ukraine, right? Or where's Chernobyl? It is in Ukraine, right? Yeah. It looks to me it's in some abandoned industrial area. Don't do this, okay? Don't go to Russia. Don't do this. If you see the guy like the very beginning with his shirt off and he asks you to attach yourself to a limousine, don't do it, okay? If you're over in Russia and these guys are talking to this, don't do this. No one gets hurt in this one, but still, just don't do it anyway. It's scary. Don't do that. That's really scary. She's just holding on, right? She's got a little swing in between her legs, and she's just holding on. The same group, slightly different. This one looks painful. My God. that one, I think she felt some impact, right? Her body twists a certain way. I don't think it should have twisted that way.
Super,
That's what you do in Russia for fun, I guess. All right. It's a YouTube Monday kind of day. Okay. Let's keep going. Let's keep going with this. Polar coordinates. Okay. So it's just the same idea that we've done before. I mean, these problems aren't bad, right? I mean, hopefully you're seeing that. They're not too intense. So again, polar coordinates are different than normal tangent. We have this R that's pointed out like this, and then our coordinates keep going in this direction, ER. And then this one right here is E theta. Right. What's different about this one, the way I've got it drawn right here, it actually lines up with normal tangent pretty close, but it doesn't have to. If you're in a different place, if you're over here, for instance, right, our R would be pointed off there, and our theta would be pointed off over here, right? So our coordinate system is different, right? But this is it. When you do it this direction, this R, the radius of R can be changing. It can get bigger and smaller, right? It can have velocity in that direction. It can have acceleration in that direction. And then theta can be accelerating as well. And so you can have an alpha and an omega associated with it. And so the velocities were this, which we're not going to use for this particular derivation, but our accelerations will, right? R double dot minus R omega squared is acceleration in the R direction, and then R alpha plus 2R dot omega is acceleration in the theta direction. So when we do this derivation, you just look at the different directions, some of the forces in the R direction. We're going to do that same thing. We're going to sum up we're going to draw our free body diagram. Then we're going to look at our coordinates on there. We're going to sum up all the forces in the R direction, and that's equal to mass times acceleration in the R direction. Now the acceleration in the R direction is both of these things, mass times R double dot minus R omega squared, right? And then in the theta direction, we're going to sum up all the forces in the theta direction, and it's going to be mass times acceleration in the theta direction. Now acceleration in the theta direction is everything, right? R alpha plus 2R dot omega. It's got the R alpha, the tangential acceleration, plus the Coriolis acceleration. And then if we do this thing in polar coordinates, or not, cylindrical coordinates rather, then you could pick up a z direction. So I think one of the problems we're going to do today actually both problems have a z direction. It's actually cylindrical coordinates what we're going to do. So that's that, right? Pretty straightforward. The only thing is that our accelerations change from the previous ones. Okay. 2 kilogram collar is on an inclined rod as shown. There is friction on that rod, okay? What's the minimum constant angular velocity so that the collar does not slip down the rod, right? So this thing is spinning around like this, right? So that you can see this is a 3D problem. It's spinning around like that, right? If you can imagine if that thing goes really fast, that collar goes sliding off the top of it, right? It'll go shooting off to the right there. And then if it goes too slow, it'll actually slowly go down the rod. And so it's trying to find the minimum constant angular velocity so the collar does not slip down, right? Because if it's just sitting here, this collar right here is just going to slide down. And so we're going to speed that thing up. Again, if it goes too fast, it goes flying off that direction, but we're going to find the minimum so that it does not go flying off of there. Or sorry, the minimum so that it does not slide down. You could solve for the maximum so that it doesn't slide off, right? But this particular one says the minimum so it doesn't slide down. Okay. And then again, there is friction associated with it. So what do we start with? Free body diagram, right? FBD. FBD. Okay, we isolate our mass. Look at everything that's acting on it. What do I got acting on? There's a few things. Somebody should always just shout out gravity.
Gravity.
There we go. Like, gravity, right? Gravity's always going to be there. Well, it's not always going to be there. Sometimes it's not. But for the most part, if we're just dealing with problems like this, there's going to be gravity being there. So this mass times gravity going down. Okay, what else have I got? Friction. Oh, which way is my friction going to go? Yeah, up and to the right. Because we're trying to figure out the minimum so that it doesn't slide down. And so friction is going to be helping us there. If we were trying to find the maximum so that it doesn't slide up, then our friction would be going down to the right. So we're going to we're gonna find the cusp of it just sliding down. So we want the friction going up and to the right. Try to line this thing up so that it's kind of, okay. That's our friction. Mu static times the normal force is what that friction force is going to be. What else? I got one more. Normal. Yep. That's close enough. Normal force. Okay. What we haven't talked about is what coordinates, right? Well, obviously this is going to be a polar coordinate problem or a cylindrical coordinate problem. So one way to kind of, this is the first time we're looking at this, it's sometimes nice to let's kind of think about how this thing is traveling, right? This thing is traveling around in a circle, right? It's rotating around like this. So that collar is going to be traveling around in a circle. So we're going to let's look down on it from above just to kind of, oh my gosh. I hate when I can automatically draw circles, but sometimes they're so bad that I can't even draw one. Okay, so that it's traveling around a circle. That collar will be traveling around like that, okay? And so, again, this thing's gonna be polar coordinates, or cylindrical coordinates. This right here is gonna be the ER direction. Right, because there's an origin. Let's go ahead and talk about, there's an origin here. And then R is pointed out to that particle, right? It is traveling around. It's traveling around a circle. So ER is also moving. Remember that in polar coordinates, those things are not stationary, right? They're moving around like this. So we're gonna draw this thing in its current state right here, where it's kind of off to the right, and so that it'll line up. If it's over on the other side, it all stays. It all works that way through. If we go over there too, so we're just gonna draw it in its current position over there. So ER is going that direction because it's just a continuation of R. And then E theta is going to be increasing in the increasing theta direction. So we'll assume that it's rotating that way. So this is E theta direction. Okay, and then we need a Z direction. Which way is Z going? Into and out of the page. Okay, Z's going into and out of the, well, from the top. From the top, it's going down, right? Because we're looking down on it. So then let's come down here to our free body diagram. Where do these coordinates line up down here? Where's ER in this diagram right here? Right here.
I have a question.
Yeah.
When you're doing polar coordinates, do you use the right-hand rule to figure out where Z is going, or do you just choose one?
We get to choose them. So Z is going to go in and out, right? So this isn't Cartesian coordinates. Right-hand rule is kind of in the Cartesian coordinate realm of things, and so this we're just going to choose which direction Z is going.
Okay.
We'll see it play out.
Okay, sounds
Yep. Okay. So ER and E theta are going like that, and then it'll just be perpendicular to the plane made by ER and E theta. It's just perpendicular to it. But anyways, come back here. So ER is going this way, right? Because that's the top view. This is the side view. So it'd be like looking at this thing going that direction, right? So where's E theta on this? Going into, in this particular case, it'd be going into the board right here. That's E theta. And then Z direction, we get to choose it right now. Which way you want to have Z? Have Z go up that direction, right? So that would be like coming out this way, okay? And so let's put that coordinate on there. So you won't put E theta on there because it's just going into and out of the board. But Z, the K direction, is going that way. It's important to get that. So it's just perpendicular to the plane made by ER and E theta. We're going to assume that the positive K is going up. We could assume positive K is going down, but we're putting positive K is going up. We're going to see that. That's an important concept to get there, is to see that aspect of it. Right? That's where this is cylindrical. Right? So you can imagine if that thing goes up and down, it would be accelerating in the Z direction. If it was going up, it would be accelerating positive Z direction. If it's accelerating, if it's moving down, it would be accelerating down. So those are all the components. Still not done yet. We have to put in all of the coordinates that we need, or all angles. They give this to us as a 3, 4, 5 triangle, which I love 3, 4, 5 triangles. No, it has to be ER. So it's only going to be ER coming out because this is the, right? If you're at the origin, it's coming, R points to that point, right? It goes out to there, and then ER just keeps going with that, okay? And then E theta is always perpendicular to it, so it's going that way. And so if we come over here, right, that's like looking, if we look at this thing going this way, if I'm down at the same plane and I'm looking at it, then ER is going to be pointed to the right. E theta is going to be into the board. If I looked at it, ER and E theta are always traveling with it, right? So then even if I looked at it up at the top, I would still be, and then I would draw my free body diagram, like ER would be going that way and E theta would be going back in. And then there's over here, what's that?
I said that doesn't make sense. To me, it looks like E theta should be going in the normal direction, and ER would be in the theta.
So we're not looking at, if you'd be right if we were looking at it this way. If I was looking back at it that direction, then E theta would be to the right. But I'm looking at it, I'm an observer, I'm a person right here, right? And I'm looking at that point right here, and then that guy's pointed to the right. Right? Okay? If I was over here looking back, then you're right, E theta would be doing that, but then it would all work that way. It would just be weird. Okay, because some of those forces would be acting in weird places. You'd be looking at this not from this angle. You'd be looking at it from, straight on, and the collar would be coming right at you like that. It'd be kind of a weird way to do it. So it's important to get that. So stick with me here. Okay, so here we are. We're gonna go over here. All right, draw the numbers on here. I always like to leave it in 3, 4, 5. All right, this is my 3, this is my 4, this is my 5, and then this one. And this one right here. This would be 3, this would be 4, this would be 5. You could turn those things into angles if you want, but to be honest, it's easier if you leave them not angles. If you turn them into angles and you put sines and cosines, this is kind of a gift. When you see the 3, 4, 5 stuff, it's a gift to you, so you don't have to actually calculate the angle and then have a bunch of sines floating around. You can just use those numbers right there, and we'll play it out there. All right. Okay. Everybody okay? Everybody okay? Okay. All right. So there we are. There's our free body diagram. All the key parts. Right? Now we draw write our equations of motion, our EOMs. EOM. Okay. And let's do, we have 3 directions to look at. So we have 3 equations of motion, the R, the theta, and the Z direction. So we have to write the equations of motion for each of those. Some of them we need, some of them we don't. So if you look in the Z direction first, just for the heck of it, you could start with any of them. I'm going to start with the Z direction. We get some of the forces in the Z direction is equal to, so the Z direction is going this way, right? So we've got a component of the N, a component of the friction, and mass times gravity. You have all 3 of those components. So we should have 3 components in our sum of the forces in the Z direction. It's going to be the normal force times 4/5 positive plus the friction force times 3/5 minus mg is equal to mass times acceleration in the Z direction. So this is 4/5, right? Because you look at the vertical component of that leg is a 4, and so it's 4/5. So that's the same as calculating the angle and using cosine or sine, depending on how you calculate, what angle you calculated. Right, so that's kind of nice. This is what I'm saying, it's a gift. You just, well, what's the vertical component? Well, the 4 is the vertical component. The hypotenuse is 5, so it's just going to be 4/5. N times 4/5. This one, the vertical component's 3, and that's 5, so that's 3/5. Okay, so what is the acceleration in the Z direction? 0, right? If this thing is not moving in the z direction, that's what we're solving for. We're trying to find so that it's not sliding down. If it was sliding down, there would be acceleration in the z direction, but it is on the cusp of sliding down or not sliding down, so that acceleration in the z direction is 0. Okay? This is just a statics problem in that direction. Okay? I think you have everything to solve for the normal force there. This is the friction force is just mu static times the normal force. So we know mass times gravity, we know the mu static, and we could solve for what the normal force is. The normal force ends up being equal to 21.32 newtons. Okay. That's not what we're after though, right? We're after that velocity, but we need that eventually, right? If you didn't do this one first, you'd get down, there'd be a normal down there someplace, and you'd have to solve for what that normal force was eventually, okay? So we just happen to start with the sum of the forces in the z. So we can look in the other direction, theta direction. Theta direction. Sum of the forces in the theta direction. Theta direction is equal to, well, we didn't really put it, there could be a force. There could be a force in the theta direction, right? Something pushing it like that. Right, but there could be a force acting into the page, right? Either into the page on this diagram or from above there, it could be acting like that, okay? So we'll just say there is one there. We'll say there is one there. There could be. Let's just be F theta is equal to mass times A theta. Acceleration in the theta direction is equal to mass times R alpha plus 2R dot omega. Right? This thing says we're trying to find the constant angular velocity, so alpha is 0. Okay? And if this thing is not sliding up or down, if this is not moving up or down, then R does not change. And if R doesn't change, then R dot is 0. There's 0 velocity that direction, so that guy's 0. Right? And so it tells us that F theta is equal to 0. Right? So there is no force in that direction. Does everybody see that? If it was accelerated, if it wasn't a constant omega and there was an R alpha term, I said, yep, there's a angular acceleration. Well, then you'd pick up an F theta. There would be a force. There would be a force pushing on the side of this, going into the page, right? If I had an alpha, or if that R was changing, and I have the Coriolis, and there'd be a pushing from the side. But since the R is not changing, and we do not have an alpha, there is no force this direction. Okay? But there could be, but there isn't. Okay, that would, if there was that would affect the normal force as well, right? Because you'd have two components to the normal force. You'd have the one that we have drawn here, and then you'd have a component into the board as well, because that is kind of a normal force there. So that would affect with the friction force as well. We don't want to go there right now. Okay, but it would be. So that just tells us the sum of the forces in the theta direction are equal to 0. F theta. Right, still not what we're after. After that velocity or that omega of how fast it needs to be rotating. Okay, so last direction to look is the R direction. R direction. Some of the forces in the R direction. Try to make this a little bit cleaner here. Some of the forces in the R direction. So you look over what's acting in the R direction. We've got that component of the friction force and that component of the normal force. So that normal force is going to be negative, right? And the friction force is going to be positive. And you look at the horizontal component of the forces. So N times 3/5 plus the friction force times 4/5. is equal to mass times AR. And those are the only two forces acting there. Gravity's not acting in that direction. One's positive, one's negative. And then you write in that full equation for that, mr double dot minus r omega squared. Okay. R is not changing because we're trying to find it so that it's stationary, so that r is not getting bigger or it's not getting smaller. That radius is not getting bigger or smaller. It's that r double dot. That guy goes to 0. That's just 0. And there's that omega. We're after that omega right there. And so we should have everything to do that. This right here, that friction force, again, is a function of the normal force. U static times the normal force. The normal force is equal to 21.32. You plug that normal force into the N there. You plug that, I guess we'll make sure that that goes in there. That goes right there. If you plug those things in, it's equal to r omega squared. The only unknown in that equation right there is omega. And you solve for that omega. That's what we're after. The omega is equal to plus or minus, you get plus or minus 4.85 radians per second. Okay, it's plus or minus because it can rotate either direction, right? I could have that thing rotating around to clockwise or counterclockwise, whipping around that way or whipping around this way, either one. Yeah. Good question. I was just gonna get to that. It's one thing I left out. Let me finish. I actually did forget. I did forget that. I was like, oh, we should talk about that. So, right, what they give us is 0.25 meters, right? That's the distance from the origin up to that. But what it's the circle that it's actually rotating around is the horizontal component of that, right? And so instead of being the full 0.25, it ends up being that radius right there. Hold on, R. Oh, I don't want that color. Let's make it a different color. This R right here is equal to 0.25 times 4/5. So that ends up being 0.2. It's just it has the same angle to it. So that's the hypotenuse. The hypotenuse 0.25, but we just want, that's the radius right there. That R right there is this R right here, or sorry, is this R right here. Everybody see that? It's like looking down at it from above. What's the radius that thing rotates around? It's a really good point. Okay? Go.
What was your, so you're using angles, how did you know right away that normal was for, like, the triangle you use normally?
Good question. You should get used to using this. These are nice shortcuts, right? I'll see if probably about half of you, if I give you a triangle like this, we'll calculate the angle theta, and then it'll do sines and cosines, right? Well, the sine of theta is opposite over hypotenuse, right? So sine of theta is the same as 3/5, right? And so instead of writing sine of theta, I can write 3/5. And the same thing with, depending on where my theta is over on the other side, you can calculate it because it's just going to be the hypotenuse over the angle. So it'd be 4/5 on the other one, or 3/5 if it's cosine. And so what I do is the little trick here is, so for in the z direction, in this direction right here, I just say, okay, well, the the vertical leg of this is 4, and the hypotenuse is 5. So it's 4/5 times the normal force would give me the vertical component of this. It'll give me that one, right? And then on this one over here, the vertical component is 3, and the horizontal is 5. So it's just 3/5 times that. Okay. Cool. And then when we went over to this direction, we were looking at in the R direction. You got that guy and that guy. It's 4/5 because that's the horizontal component over hypotenuse, and this one is 3/5 in that direction. It's a really nice trick. Like I said, when you see a 3, 4, 5, or where I give you all the, you'd be like, yes.
I know how to use that, but like,
Yeah.
what you knew right away the normal was, see how the triangles are like super squat.
Oh, how did I know this one was like that?
Yeah,
Oh, it's just because I'm a doctor. No, I mean, this is back to it's, if you trace through the angles, right, that's, oh, we gotta work it. That's, you got not here. All right, you got, that's theta. That's theta. That's not theta. That's the same as that one, so that's theta there. And so this one ends up being theta, and that one's theta, and so then that's how it ends up being. Yep. Yeah, and then also just, it is kind of just cheating a little bit. It's like, oh, it's 3, 4, 5 that way. That one's obviously it's steeper coming the other direction, so that's a 4, 3 to go. But you can do it. It's just the same way. You can trace through which the angles are. Absolutely. You could have stopped me earlier when I would explain. That's okay. That's okay, man. Yeah. I think it's good for people to see that and go over it a little bit. And we had a couple minutes to kill anyway. Okay, that's it. That's FMA stuff. We're going to do one more example on Wednesday. Okay, that's this guy. It's actually very similar to the other one. So this is a ball on a string whipping it around. What's the velocity that it needs to be at so that it holds that angle of 85? You can imagine if you rotate it faster, that thing goes up to 90. If you rotate it less, it's more slack and it goes down further. So we can find that. Okay, then we're going to talk about orbital mechanics, which I think is really cool. We're going to take this same idea and apply it to orbital mechanics and calculate the different radiuses of satellites in space and the moon in space and all this. We're going to apply it and we're going to be able to predict those things pretty well with just like some pretty simple math and some pretty simple physics, which is really cool. And then we're moving on to work energy, okay? So your homework this week goes through this stuff, okay? It's basically FMA for the 3 different coordinate systems. That's it. It's kind of long. I think it's like 9 it used to be like 12. I shortened it a little bit. I think it's down to 9 problems. But so it started a little bit early. This is what next week's exam is going to be, okay? It's through this, okay? And then, so that's where it's always going to be a little staggered behind. We'll start work energy, but work energy will not be on the first exam. What will be on the first exam will be kinematics, particle kinematics, and then this stuff. FMA and the 3 different coordinate systems. And the way it's structured, just to give you a little feel, is there's 2 problems. One problem is going to be kinematics, particle kinematics, and one problem is going to be force, mass, acceleration. That's it. And it's just me versus you guys doing those problems, okay? And you work them all out. No short answer, no fill in the blank, stuff like that. It's just work out these 2 problems. Cool. And it'll be in class, 50 minutes, and we'll go. And then if you do have accommodations, everything should be set up over at the place to the testing center over there. So, cool beans. Break. Have a good week.